Really excited for y'all to be here today and share with y'all this automating civil grading and racking pile reveal for utility scale solar plants. I'm going to kick us off with introductions. My name is Casey Hirschman. I am a senior integration and process automation engineer here at Revamp. Have about 3 years in the computer science and data science space, and I am based in Houston, Texas.
Hey everyone, I'm Marco Alvarez-Patino. I'm a civil design engineer at Revamp. I've worked in solar since 2019, and I am based out of San Francisco, California.
And hey everybody, my name is Dustin James. I'm a vice president here at Revamp, and I lead our civil engineering team, and we're happy to have you here with us. So just a little bit about Revamp before we get started here. So Revamp is a multidiscipline engineering company. Started in 2016, so almost 10 years old. You can see some of our core disciplines that we offer. And today you'll get to see really what's one of our core values that is lived out on a daily basis here at Revamp Design. So, Marco sits on the civil team, Casey on the automation team, and together they use their unique skill sets to come up with a really great solution for what is an industry-wide challenging problem. We have about 150 employees, some of the industry's best and brightest. We have been fortunate enough to be a part of, since inception, approximately 21 gigawatts of projects that have gone to IFC design, issued for construction. And then we've also been a part of approximately 275 gigawatts of early phase development design. So a lot of experience. Really, Revamp as a company, our core mission is to be a part of this renewable energy transformation within our country and beyond. And so we're really excited to share with you some of the solutions that we are coming up with for industry-wide problems. So thank you for being here. And with that, I'll turn it back to Marco.
Yeah, I'll talk a little bit here about the layout of our webinar. So we're going to start off with talking a little bit about the basics of solar civil site design and navigating some of the challenges we've had there. We'll also talk about the challenges surrounding traditional site grading and what we have traditionally done to previously come up with earthwork estimations. And next, we're going to talk about the application of the automation processes that Casey and I have worked on and how that has led us to better workflows and increased accuracy in our earthwork estimations and additional optimizations that we've applied on top of them. And then we'll also dive into some real world case studies, so sites that we've actually worked on at Revamp and seeing the quantities associated with those. And alongside that, we're going to see the real world impact of how we have been helping our clients and how we've been utilizing these tools to design more efficiently. And finally, we'll have some time for Q&A at the end. But also, please note that you can use the Q&A feature inside of the chat, and feel free to ask questions throughout the chat and the webinar. Solar civil site design and why it's so key and why it's such a big consideration when it comes to solar site design. So the design of a solar site, the civil cost is one of the largest cost drivers when it comes to development of PV, utility scale solar. And we're seeing industry changes, and we're seeing that as utility scale solar grows, there is less and less suitable land for the development of these projects. Well, it's still suitable, but it's not ideal. We're quickly realizing that we've run out of the flat sites. There are no more flat sites. There are no more easy sites. Now everything's like terraced and just paying with slopes. And, it's up to us to, as civil engineers and engineers, designing solar sites to navigate those conditions. And we're seeing it more and more that these sites are being developed in areas that have high slopes, the parcels are fragmented, or there's flooding concerns, and those are all conditions that we need to take into consideration when it comes to designing solar sites and designing surfaces and designing plans that we can provide to our clients and have confidence in them avoiding issues with flooding or erosion control issues. And, as the market evolves, we're seeing that this is a more and more common issue, that civil grading and civil cost are one of the leading cost drivers behind a solar project development. So before we talk about workflows, we're going to get into some key terms here. I'm sure many of you are already familiar with terms like these, but just to kind of reiterate, the process that we're working through here is, like the name of the game is solar. There's a solar tracker, and the installation of solar trackers and these structures are what drive the need for civil engineering on a project. And that is specific to pile reveals. The piles are what are installed on sites to install the tracker structures. And there are minimum and maximum pile reveals that we would use on a system. And like if we look at this graphic here, there's a minimum reveal and a maximum reveal. And there is a reveal window. So anything outside of this reveal window would be a requirement that we need to either cut or fill. So that is where the earthwork estimation comes into play. Based on the placement of these trackers in 3D space, we can estimate the associated cost and volumes of these earthworks that we would need to cut or fill. And basically that's the name of the game. Place this tracker structure, find cut and fill volume. So there are implications to site grading, both to cost and feasibility. And those come into play of both from a perspective of there's an additional cost associated for every cubic foot of earth that's moved, not just from a material cost standpoint, but also from a labor standpoint. It is time consuming to move this, and if you have people driving a dozer throughout the site, that's costly. So by optimizing our earthwork volumes, we can pass on those cost savings to our clients and have a real world impact on project schedules and keep the necessity for earthwork movement at a minimum. And alongside that, if we're able to minimize the cut and fill, there's less of an environmental impact, and also less area disturbed. So if we move less of the site, that's less labor there. That's less potential to erosion and sediment control issues. So there's some flexibility when it comes to tracker systems, both from a tracker manufacturer perspective. There are different manufacturers that offer different solutions, and not just from a standpoint of you have different places to purchase them from, but also there are new systems that I'm sure you're all familiar with. There's linear torque tube systems, and there's also terrain following systems. So many, if not all, of the tracker manufacturers have their standard linear torque tube system, and they have their terrain following system. And the introduction of these new systems mean that we have to evolve as engineers to be able to produce earthwork estimates for both terrain following and non-terrain following systems. And alongside that, we don't just provide guidance to our clients on which systems to use, but we also provide guidance on pile reveal and minimum and maximum pile reveals that we would recommend to use on site, based on what we're seeing on site conditions. So I think that's also a point that Revamp really prides itself in is that we're a holistic renewable energy company, and our focus is in solar. And we have many teams that work on all aspects of the project. So we have a structural team, we have a civil team, we have a that calculates like the flooding and the hydrology and hydraulics associated to the site. So we can work holistically on a project and work together in collaboration and come up with solutions that meet all of our clients' criteria. And specifically when it comes to tracker systems, one of the big ones is freeboard requirements. So we're able to quickly iterate in-house on potential designs and pass those off to our flood depth team, and they calculate flood, and we can quickly calculate the freeboard with our surfaces and align on tracker selection and different reveal heights.
And Marco, I think your volume's coming in and out.
Okay, let me switch the mic. Okay. Can you hear me better now?
Yes, seems to work.
Okay, sounds great. All right, yeah, so I'll talk about the challenges with our existing solutions. There's a well-known, beloved CAD program that we previously used at Revamp to design and estimate our earthwork quantities. And there's challenges associated with that program and traditional methods. So specifically, this is something that's very like near and dear to my heart, is because, my knowledge and understanding of applying different solutions came from a pain point, and that pain point was difficulty with this CAD program working on solar sites. So because it was so difficult and time consuming to use CAD to design solar sites, I ended up looking at different solutions and working on different models to try to find solutions that were not CAD related, because there are so many pain points there when it comes to not just processing times, and maybe the program will like break or like fatal error. But it's also things like, you need to have experience and knowledge and know how to use these tools. And, you can't just quickly train somebody how to use these solutions. So there's definitely a gap in the market when it comes to something that's holistic. I think there's a lot of PV manufacturer or PV design softwares that have their own solutions, and I've also used them before, and I think I can speak from experience that a lot of the time these softwares are not as accurate as we would like them to be, or as accurate as we need them to be in order for detailed construction design. So we cannot rely upon them. Yeah, and because there's no tool available, it led us as a team to try to develop something ourselves. So I'll talk about the racking specifications as well. And I think that one of the biggest disconnects in construction, or a common one that I've seen, is that we don't, the manufacturer may specify something, but the in-field conditions are completely different. And we're seeing that, like in a perfect world, in an ideal scenario, yes, these tolerances are fine, but more likely it's common that we're going to run into something in the field, whether it's like a small tolerance issues when it comes to surveying or feathering or something like that. And having the ability to be able to work in those tolerances and work in those specifications in a way that we can alter them and suit them to our clients' needs is very important to us. And it's something that we've been working on and continue to work into our tools. And I would also say that it is common that, like, just to give an example, for a tracker manufacturer that has a terrain following system with a bend of 1 degree. Our clients, our EPC clients, will actually lower that tolerance to give themselves more wiggle room in the field. So we actually design a lot of times to maybe like 0.75 or 0.85 degrees of allowable bend in a torque tube instead of, the more refined version that the manufacturer specifies, just to be able to suit those on-field needs for our clients. So I think here's where the handoff kind of occurs, and like the need for this tool was born out of the need to quickly iterate and quickly adapt to both like a changing market and changing needs of our clients, and also the inaccuracy and the pain points that we had with existing solutions. And when I first came to Revamp, I came with some experience of working on tools like these before, and previously, I've worked on linear regression calculators to design civil sites, and for some time I was working in a GIS-based program and designing solutions to fix problems that way. And I would run into issues with the GIS processing speeds, and eventually that led me to work on a Python script that I inevitably ran into issues on. And because we have so many resources in-house at Revamp, specifically Casey, who is a wizard at Python, I reached out to her and she was able to help me on this problem, and I explained the problem to her, and that's kind of where it began. The communication there and the ability for me to reach out to her and kind of work on a solution together. And I think it's been maybe close to 2 years now, and we have a tool that we utilize every day now at Revamp, and we've designed several sites with, and I'll pass it off to Casey to talk about that.
Awesome. Thanks, Marco. Yeah, I think it's just such a cool example of how cross-functional collaboration and taking people in their various subject matter expertise can really create a powerful solution to a problem. So in this next section, I'm going to walk y'all through the algorithms at a kind of high level, and then I'll hand it back to Marco and we can look at actually what those algorithms have done for us and some examples, which is the really exciting part. So, make sure you stay tuned for that. Okay, so what are we actually doing in Revamp to make all of this happen? We're using a combination of QGIS and Python, which Python is just a coding language, and some of the inherent Python libraries that are very commonly used in computer science and data science. And then what are our engineers actually doing? They're doing some pre-processing in QGIS, which outputs a CSV. And then they come to this GUI you can see on the right of this slide, and they have some optionality. They have some space to put different manufacturer specifications, hyperparameter tuning, which we'll talk about in a little bit. And then that results in a new CSV that they'll pull back into QGIS for some post-processing. I think it's important to note here that this software is a complement to engineering. It does not replace engineering. And we'll talk about why that is in a little bit. But ultimately, this is a tool to help speed up our design and support our engineers. But engineering is still very much a part of what we're doing every day in Revamp and crucial to this overall process. All right, before we get into the algorithms, let's kind of make sure we're all speaking the same language here. We've seen this kind of side profile when Marco was showing us that min and max reveal and the cut fill. So we're kind of coming back to that. And we have our different pile points and the northing associated with them, since our trackers run north-south. And those northing, we're going to call X naught. And then we have our existing terrain, which is in orange here. That's our Z naught. Now I have two algorithms I'm going to talk to you about where we're taking our X naught and our Z naught, and then we're doing some fun things, and we're producing our Z reg, our Z regression. And that's the basis of our design. Then I have a third algorithm I'm going to talk to you about, And that one is solely based on optimization. And that one is taking our Z-reg and we're working on our offset to get our top of pile elevation. And we're trying to find the top of pile that is going to ultimately lead to the lowest cut fill, the lowest earthwork required on a location. Let's look at our first algorithm. This algorithm is specific to linear torque tubes. This is our linear torque tube solution. Now, this is a weighted regression. Talk about regression, basically just a fancy word for fitting a line of best fit. So if you think of a scatter plot, you know, we've all worked with scatter plots at some point, and you're just trying to fit the line that best, you know, fits most of those points. Now, what is the scatter plot we're looking at? That is, take us back to that X naught and our Z naught, our pile northings and our existing terrain. And then we're using regression to find our Z-reg. Now, there's a difference between standard linear regression and weighted linear regression. And we'll talk about why that matters in a second in our solution, but standard linear regression, just that line of best fit. And then you have the weighted linear regression. And that regression allows you to take certain points and place more importance on those points when it is fitting that line. And that's what we ultimately use for our design is the weighted linear regression. Now, why does weighted linear regression outperform standard linear regression? If you look at our little visual here on the right, we see our existing ground, that Z naught in red. Then you have our two different solutions. You have our linear regression in blue and our weighted linear regression in black. And in both of these visuals, you see kind of two lines there, right? And then especially with the blue, you see that big kind of cliff face between the two lines. Now, these are two neighboring trackers. And when we start getting into this hillier terrain that Marco was talking to us about, you really, if you're using just a standard linear regression, because so many of your inner piles can, you know, are on a hill or in a valley, you really start shifting those lines. And you really see that on this bottom visual here, where you have this big cliff between the two neighboring trackers. And this is actually not a feasible design. And the reason there's rainflow issues, erosion issues, and manufacturer specifications that basically don't allow for that kind of difference between neighboring trackers. So when we use our weighted linear regression, we actually place more importance on our end piles than our inner piles. And this is one of our user inputs, basically how much weight they can place on those end piles. And because neighboring trackers end piles are generally have pretty close terrain, now you see our result in black, which is actually a much more feasible, reasonable, realistic design. Okay, so that's our linear torque tube. Let's transition to our terrain following systems. Now, this is those trackers that can allow some bend, right? And this is ultimately becoming more common and is a more difficult solution to design to this terrain. So we use this thing called dynamic programming. And dynamic programming is just it's a common computer science algorithm applied to a bunch of different functions, but here we're applying it to our terrain following trackers. And basically, what does dynamic programming do? It takes a larger problem and breaks it into smaller subproblems, and then it just iterates until it reaches some sort of convergence. So for our subproblems, we're starting with that Z naught, the existing terrain, and we're looking pile by pile. And at that single pile, we're looking at its neighbor piles. And then we will move adjust that Z-reg so that we do not break our bending manufacturer specification. So you can see in this first visual here, we have our Z naught in orange, and we see our first iteration, that blue pile point. And you can see that existing terrain, basically the slope was too severe at that point, so it would have been out of manufacturer spec. It would have been out of compliance. So we moved that point just a little bit, and now it's in compliance. Now, we keep doing that process. You can see our second visual in the middle here, and you can see a few iterations, what's starting to happen here. But as you might have thought, once you start doing this, right, we had our first point, it's good, but then we moved our second point. So now maybe that first point is back out of compliance. So you have to iterate through the entire tracker, potentially multiple times, until you converge to where no point is moving and everything is in what's within spec. And then you get this visual on the far right. And you can see how closely that aligns with the terrain and ultimately, a design that we're happy with. Oops. Okay. Now comparing these two results, our linear torque tube and our terrain following solutions. You can see in these visuals here, you have the weighted regression or the linear torque tube results in blue, and then our terrain following or the dynamic programming results in purple. And that little kind of alleyway there, that window, is the min and max reveal that Marco had talked to us about before. And then you have the different black points in there. Those are our pile points. So any point that is outside of that window, that little alleyway, means cut fill has to happen. And you can see that with the terrain following solution, there is much fewer, if any, instances of pile points that would require cut fill. And ultimately, the big thing here is the optionality this allows us, right? We have two solutions that we can quickly design upon and kind of investigate, work with our clients to say what is going to be the best solution for them. Okay, so those are our algorithms. We talked about going from the X naught and the Z naught to our Z reg. Now we're going to transition to our third algorithm that's solely focused on optimizing the location and reducing the cut fill. And that algorithm we use is called simulated annealing. Now, this is a common data science approach that it's a probabilistic optimization method. It's trying to find global minimum in a complex space that might have a lot of local minimum. And like, what am I even saying? If you look at this graphic here on the right, imagine that is a field of hills and valleys. You have a local minimum, but you ultimately want to find your global minimum. And it does this through a series of exploration and exploitation, which we'll talk about in a second. And ultimately, we're trying to reduce our cut fill. Okay, so let's think of this as an analogy. We have imagine this landscape full of hills and valleys, and each point in this landscape represents a potential solution, a potential offset for us. And then the height of that hill or valley reflects how good or bad that solution is. So how much cut fill you might have on location. And imagine you are blindfolded and dropped into this landscape, and you're just taking steps, trying to find the lowest point in this landscape. Now, you always want to exploit. If you get a better solution, you take a step and you reduce your cut fill, you want to accept that solution. However, we also want to explore, because say you randomly got dropped and you end up in this local minimum, we don't want that. We want our global minimum. So sometimes you have to explore a little bit and you have to accept a worse solution to improve on the other side of that. So that's when I was talking about hyperparameters, that's another user input that these are inputs into the algorithm that can control how much exploring versus exploiting you're doing. And ultimately, we're just trying to not get stuck in that local minimum. Okay, so moving out of analogy world into what does this actually mean for us? Again, we're just we are adjusting those tracker offsets up and down to reduce our cut fill. Now, we are doing this on a tracker by tracker basis, and I'll explain in a second why that matters. But we're looking at a single tracker, and we continue until we either get to zero cut fill, or we've gone through a certain number of iterations and we're confident that we've probably minimized as much as we can. And then we'll run multiple cycles. So basically blindfolding, we're dropping you in multiple different places in the landscape. And you can see in these visuals here on the right, say our first iteration, this random offset, and we have only one pile that requires cut fill. It enters the terrain in that reveal, or sorry, one pile that does not require cut fill. It enters that terrain in the reveal window. Second iteration, we actually get better. Now we have 3 piles that enter the terrain in that reveal window. Third iteration, not good. Everything would require cut fill with this solution, so we don't want it. And the fourth iteration, we're probably at our optimal designed here. So that's what's happening. Up and down until we reduce our cut fill. Now, trade-offs. This algorithm can substantially reduce grading. It's great. However, it doesn't automatically apply these manufacturer constraints. So like east-west, north-south, those neighboring tracker situations, because it's only looking at a single tracker, you can end up in a situation where you're out of spec. So again, that's why this is a complement to an engineer's work. It does not replace the engineer, and there is post-processing required. And ultimately also the algorithm's effectiveness is based on these user inputs, these hyperparameters, because you can spend, for sure find your global minimum, but you could spend an immense amount of computational power finding it and sit there forever waiting for a solution. Or you could choose some poor hyperparameters where you don't actually find any of your global minimum. So that's another thing the user needs to understand what they're doing. Now, that's the algorithms, that's the how. And I'm going to hand it back over to Marco to talk about the what that actually means, which is definitely the most exciting part here.
Thanks, Casey. No, I thought the algorithms were super exciting too. I think the application of the algorithms is really what like drives it home to most people. And we're gonna dive into some like real world sites now that Revamp has worked on and look at the differentiation between our different solutions here. So first slide, and I'll also say that we're going to be looking at two different racking solutions, the linear torque tube racking solution and the terrain following racking solution. So the first two that I'm going to show are going to be linear torque tube, and the last two are the terrain following systems. And there are associated costs to both. So keep that in mind as well with these numbers. So the first one, we can see here that this is the traditional grading methods and, the proprietary beloved CAD software that we've, used and loved before. And we can see that the impacts from a quantity standpoint and from a material balancing standpoint are pretty significant. There are close to 400,000 cubic yards of earth moved, and the impact of the 2D area is quite substantial. I would say as well, too, we can speak a little bit to the time taken to actually come up with a solution. Was considerable, and it was kind of like the standard that we'd have at Revamp, that we'd have these solutions done in our CAD software, and it would take us a lot of time to produce the solutions and produce a suitable site design. And, as I spoke about earlier, as the sites increase in size and as the terrain becomes more and more complicated, that's just makes it more challenging for us to try to design solutions for that. So in the next slide, we'll look at our weighted linear solution. So here is the application of the algorithm that Casey spoke about earlier. And we can see that it's almost like a halving of the quantities used. So we went from almost 400,000 cubic yards moved to 200,000 cubic yards moved, and that's like huge. So, like big cost savings there from the perspective of there's less earthwork to be moved, there's less labor, and, maybe you don't have like import or associated cost to the importation of the actual material. And overall, we can see that it's a much better solution than the one that we had before, and we can, deliver it at a faster timeline and have more time spent on design and the actual engineering work than working on CAD. And next, I'll dive into the terrain following solutions. So what we're seeing now is the application of our terrain following algorithm and the use of a terrain following system on the same site. So we're looking at the same site. This is a site in Colorado, and we were tasked with looking at different solutions for this. And we can see that there's a substantial reduction in the earth moved overall. So we have, again, and that's huge. Like that's a big saving in terms of material and costs and impacts. And, we want to keep the impacts to a minimum also to make sure that we're not causing unnecessary erosion or soil disturbances and, keeping our topsoil. That's a big thing on these sites. But we can see also that there's another optimization that we can apply that Casey spoke about earlier, and that is the terrain following and simulated annealing approach. So this is the application of our optimization algorithm, and we can see that we drop almost 40,000 cubic yards of earth moved, and we didn't change anything in the system. There's no movement. It's just an optimization on the placement of the tracker. And like Casey said, we can have these hyperparameters and we can tune them to something that we believe is suitable. And as we work more and more of these sites, we get more and more data and more knowledge and experience on what are good parameters to use for different site conditions, and really be able to speak in a knowledgeable way on, like earthwork estimates and earthwork impacts that we're going to see on a site using not just a terrain following system, but different systems. And we've worked on sites where we've used both as well, and we have the ability to adapt to both. So next we'll also look into some profile views. So I think the profile view is really good to kind of see how the algorithm is working, and that it is working as well. So you can see that it's working as expected. There's some sort of normalization occurring at the terrain. There is a cutting of the hill and like a filling of the valleys in like a very smooth way. And, this is all to be fit within manufacturer specifications of whatever they say their allowable bend tolerance is between torque tubes, and we comply with that. And you can see really well from like these cross sections that they're steep hills, and they're being normalized to a allowable bending tolerance. And that's a site in Colorado that we worked on. So this one specifically is a site that we worked on in BLM land. And, I think also with different projects, there's different concerns and different priorities, and having the ability to have a tool that is able to take those into consideration makes us really stand out and makes us be able to adapt to our clients' needs. Specifically, this one, there was a big need to minimize the 2D footprint of the land disturbance because it was such vulnerable land. And, we came up with different solutions to try to optimize the outcomes for it. And, like we can pull different levers within our system and our tools to try to optimize certain outcomes. And for this, we see that we use a terrain following system, and on top of that, we also used quite a substantial reveal range, and I think this was a specific portion of the site, and we can also tailor our recommendations for specific portions of the site and have a differentiation made there on maybe you go for a bigger pod reveal there and it's not a substantial cost adder for that section of the site. If the necessity is that we need to reduce 2D footprint there. So I'll talk about the real world impacts as well and how we're using this at Revamp every day, day in and day out. So one of the biggest impacts is that the design cycles are able to be sped up, and we can lower our engineering load and free ourselves up and have more design bandwidth to work on more projects, because our tool is able to take out so much of the work that we did before in terms of like balancing sites or something. And if we have these optimization tools and processes built in, we can work on more projects and increase the efficiency that we perform things at. And at the same time, we can offer more options to our clients, within the same design process, especially early stage. We can provide estimates that are, we're very confident in an early stage, and not just for one design, but for multiple designs. And, we see that more and more as well as industry changes, that there's more of a need now to come up with these numbers quickly and also provide options for different areas. And that's something we've really been working towards and catering to our clients on, is the ability to not just provide one solution, but the ability to, if it's an early stage design, we can get them comparisons between different scenarios. One of the biggest impacts as well is the data-driven approach, specifically when it comes to the pile reveal optimizations. And this is a bill of materials from a site that we worked on in Texas, where we really helped drive them get their steel costs down based on some optimizations we were able to do to lower the reveal heights. And because we have the data readily available to us, and there's some sort of data component to every single pile on site, we can look at what's happening at different areas of the site for every single pile and really come to some determinations by some expertise that we have, and also the data that we have at hand to be able to say, is this the minimum pile reveal that we can go to, or can we go lower and still meet freeboard requirements? And what can we do throughout the site to optimize these numbers? And ultimately, if we're able to drop average tracker height even by like 2 to 3 inches over 130,000 piles, that's a huge cost saving. So it's something that we're leaning into, and we continue to develop as the need arises. And this is what I spoke about earlier as well, the cost scenario comparisons, is that we can offer solutions to different designs. And this is a comparison between the linear tracker system and the terrain following tracker system, and their costs associated to different tracker systems. The terrain following tracker system is not, it's not a cheat code. It costs more money. That's what they don't tell you sometimes, is that you're gonna have to pay more for terrain following. So the money that you're saving on the earthworks, you might have a more expensive tracker. So being able to let our clients know and do the work to see where we could actually utilize those terrain following systems and have a real cost comparison between the two systems, and offer differentiation in terms of maybe we're able to offer or recommend a terrain following system in a portion of the site, but maybe non-terrain following in a different portion of the site, is a great benefit. And this is also like a big impact, the flexibility around and across racking manufacturers. So I'll say this is also kind of important because, as maybe some of you may have read or heard or seen our CEO, Tyler Nelson, speak to ENR on how Revamp has really leaned into adaptable design strategies. And that remains one of our key strengths in not just our tools, but Revamp as a whole, is that, in a changing landscape, we're able to adapt. And, maybe there are tariffs to a specific racking manufacturer or steel, or something unpredictable occurs, we're positioned to adapt and resolve those issues as they appear. So just to put a bow on things and wrap things up, civil site design is foundational. It's critical to PV project success. It's one of the biggest cost drivers, one of the biggest limitations of a site. And we have issues, and we've had issues before with traditional methods to come up with earthwork estimates and solutions. And because of the nature of Revamp and how we're structured and our cross collaboration, Casey and I were able to work on a solution together that has an algorithmic approach to solving our civil site problems, and really optimize the workflows and really change how we do work at Revamp. And exploring those case studies really drove that home on how important this algorithmic approach is, and how much differentiation there is between not just different systems, but different algorithms, and the optimizations that can be further had by using those algorithms. And I think just to wrap it all up too, is that it's not just these systems and tools that we have in place now, but it's the work that we do at Revamp every day, and it's the work that we do cross collaboratively that really helps set us apart. And that within our tool set itself is the ability to inevitably there are changes to racking systems. There's changing client needs, and as we grow and as the industry grows, our tool sets grow alongside with it. And yeah, I'd really like to thank everyone who made it to the webinar today, and I'll leave some rooms for questions.
Yeah, thank you so much, Marco and Casey. That was awesome. Fascinating stuff, and we do have quite a number of questions. So with the time we have left, we will try to get through as many as possible. I'll just start with at the first one and kind of go through here. So Jackie, great question. It's a two-parter. So Marco, if you want to start with this one, do you account for the max slope allowed between rows?
Yeah, I think that's a good question. I mean, I assume it would be taken into consideration like east-west, or there's also a specific manufacturer constraint when it comes to like linked rows. So I would say like yes, we do, and the row connection is very important when it comes to specific racking manufacturers, and different racking manufacturers have different specifications, and I think that's also something that's like important on being part of the construction of these projects, is that we have direct insight, direct contacts with these racking manufacturers that like nobody else really has, like us and our clients. So when something new occurs, or there's like a new specification, like we're the first ones to see it, and I don't think it's something that like a traditional tool or like somebody that's not in industry would be able to kind of keep up with. So yes, it's something we take into consideration.
Yeah, and really the challenge has been the really great thing about this tool is its dynamic nature, because what we see is that between the racking manufacturer, the EPC preferences, and then the owner's scope of work, between the three of those different groups, there might even be a civil subcontractor that has preferences. The ability to create dynamic features within the tool has been really helpful for us. Second part of Jackie's question, Marco, or any terrain how do we address terrain that's immediately outside the array?
Yeah, that's a good question. The immediately outside the array. Um, yeah, like I think that has been a question of, like working with our clients to have specific specifications when it comes to not just array grading, but also the terrain outside the site. I think currently, like our main focus is array grading and within the arrays, and we use other tool sets for outside of array grading.
Yeah, and the edge condition, that's so varied. And when it comes to civil design, right, there's so many considerations between if it's adjoining an access road, a stormwater feature, if the contractor wants to clear all the way to the fence, there's lots of different considerations. So that's usually for us, Jackie, it's a post-processing piece that our engineers are doing within Civil 3D. John, he has a lot of questions here. Thank you for all your questions, John. First one is, does the program give you the cut fill volumes, or do you get them in QGIS, I guess is the question. Where do our volumes come from?
That's a good question. I think, we need to have some sort of way to drive our algorithm. So there's a portion of these volumes that come from the process itself and like the tool itself. So those are built into the algorithm, but those numbers are not like volumetric. They're more so like a vector, change in distance between proposed and existing conditions. So there's a way that we have that built in, and early on we have those. It's like a series of points, and we have cut and fill for those points, but it's not a volume. It's like a distance, and that's where the post-processing tools that we have built come in, and we have different solutions for that.
Exactly. And then another one from John, does this program try to balance a site at all? The case study seems to not balance, but is cut heavy. Maybe this is intentional.
Yeah, that's a good question. Yeah, it's the balancing of the site. Sometimes we have different solutions. There's levers that we can pull inside our tool to try to balance more of the site. And we could try to balance by like a tracker by tracker basis, but we've seen it be better to approach these things like holistically. So a lot of the times we have other tool sets that we'll use to balance sites after our tool does the initial run. And then afterwards, it's more so like a check kind of thing. And we use this new service that we've balanced and see if it passes our conditions.
Exactly. And then how quickly can we provide results after creating, receiving a proposed solar layout? So one of the cool things that, John, I can answer this one, is that also, at the early stages of a design, this solution is also pile location based. So our team there's a script function that's written to locate piles, based on, what we understand of the racking manufacturer's spec. And then we can create a solution pretty quickly after that. Marco, I think probably a day or two turnaround, typically, if we're just doing raw cut fill numbers for the entire site. Would that estimate be realistic?
Yeah, I'd say that's about right. Like for preliminary stuff, I think, detailed design can be a little bit more challenging with sediment basins and other considerations. But yeah, we've seen like bid stage stuff go out in like a day or two, with multiple solutions as well. Of like we can stack the linear with like terrain following and different review windows and stuff like that. So
yeah. Yeah, we understand the need for speed and optionality for sure. We've got another one here from Jake. Thank you for all the great questions, everybody. What kind of maximum power reveal does the program allow? I'll start with that piece.
Yeah, I think I see the question. So I'll speak to the pile reveal restriction like a little bit. I think the our program focuses on there's like a little bit of engineering on the front end and some expertise that we have to set min and max pile reveals, and they are kind of set at a limit, and that's kind of that's fixed. So it's not necessarily like changing you can't have a solution where you're outside of your pile reveal length that you've specified. So then that necessitates grading. So that's where the grading estimate or the grading portion comes in. That if we say that's 4 feet min reveal, 5 feet max reveal, that's what the site's going to be. And in order to comply with those conditions, we grade the site.
And I'll add on to that too. That's one of the inputs that the user can use into the program. So based on the initial design work for those decisions, then you transfer that into the program via user inputs.
And just to highlight, Jake, this solution is not a structural pile design solution. So I think the other parts of your question, really what we're looking at is a grading solution here based on pile parameters that are provided, if that helps. We've got another one from John. John B. Has Revamp have we met with any racking manufacturers to gain approval on the algorithms that they meet their requirements? For example, ATI, Nextracker, Nevados. Marco, I can take that one unless you'd like to.
I mean, I guess, yeah, you can take that one, Dustin.
Yeah. Yeah, so we definitely have relationships with racking manufacturers and certainly, always work to understand their installation specifications. And so, part of the work of finding this solution is making sure that any installation specifications that are distributed with, during the design phase, we make sure to read those, understand those, and how they may impact the site, and then apply those within our tool. So that's one of the things I was mentioning that, when it comes to, if there's a new memo that's distributed, let's say from like a next tracker or something like that, it's like making sure that we understand how it gets applied to the design. And the dynamic functionality of this tool allows us to, add to, we can add a new algorithm, we can create a new script function that would calculate maybe a new manufacturer's need. So, but good question. And then Sydney, thank you. What does the workflow look like when using the combination of dynamic programming and simulated annealing for terrain following trackers? I think, Casey, this one would be for you.
Yeah. So basically, this is another user optionality. If they want to add simulated annealing on top, you could actually add it on top of the weighted regression as well. So it's really a separate step. You do the weighted regression or the dynamic programming to get your linear torque tube or your terrain following initial design. And then simulated annealing is like something they can add on to then optimize that cut fill. It's like a totally separate step in the workflow after the initial design is set.
Awesome. And then John M., thank you for your question. I think we've got 2 more minutes and 2 more questions. So let's see if we can knock it out. Does your algorithm analyze at pile locations only, or does it also verify topo and clearance requirements between piles? Marco,
Yeah, I
you
can
want to
take that one. Yeah, it's a great question. Yeah, so I think to begin with, our tool is based on like a database approach that has pile points as databases, and we run those through Python. So initially, it's just a database pile points approach. So yeah, the analysis only occurs at pile locations. And I think that it's the post-processing that is able to take into consideration the topo and clearance requirements between piles. So it's more than just like ensuring compliance at pile location. It's true that you have some sort of clearances occurring. So if there's like a ditch or like a maybe berm is usually the scenario that we run into. If there's a berm running between piles, the program's not going to capture that. So yeah, we've built out other tools that are GIS based and geospatially located to be able to find those clearances and ensure that those clearances occur. So there's post-processing checks done on top of the tool that we already have, and after those checks are done, if anything is out of compliance, it's fixed and ran through the tool again and compliance ensured.
And Marco alluded to one of the exciting solutions we provided for what might be of interest to this group is a site with farm terraces. Those farm terraces that are existing on an agricultural site are really great for erosion and sediment control. And so we came up with a solution to maintain and keep many of those berm features on site and meet the racking tolerances. So really, really cool opportunities. And then Sydney, last but not least, do you take into account a northing adjustment based on torque tube slope?
Yeah, I think that's an important one. So that's a common requirement for a lot of tracker manufacturers, that there needs to be pier spacing adjustments based on slope conditions. And that's another thing, that's another one of the post-processing checks that we take into account. So I think, really driving the home the dynamic nature and the data-based approach is that we focus on the databases and having the databases set up to then be able to provide and create more optimization algorithms or additional checks that we see fit. And as the industry changes and there are more needs, we're able to adapt to those needs and create custom tool sets that ensure compliance.
Awesome. Well, I think that's all we have time for today. Thank you all who were able to join. And again, thank you to Marco and Casey. Wonderful job. It's been so fun to watch you guys create and develop this tool. So very exciting.
Yeah. Thank you, Dustin. Thanks everyone.
Thanks everyone for coming. Bye.